Hello and welcome to another episode of Maths Whenever. In this video, we're going to see where the three trigonometric ratios of sine, cosine and tangent come from. Along the way, we will show some of the very practical applications of trigonometry. We will also prove a very simple trigonometric identity. We'll see how a calculator calculates the sine, cosine and tangent of angles. And finally, we will use some relatively simple trigonometry to calculate the value of pi. Trigonometry is one of the oldest branches of mathematics. The ancient Greek astronomer, geographer and mathematician Hipparchus is credited with compiling the first trigonometric table and is described as the father of trigonometry. Since Hipparchus's time, mathematicians from other nations have also contributed to our modern understanding of trigonometry. Trigonometry comes from the study of triangles. Triangles are two-dimensional shapes that have three side lengths and three interior angles. Trigonometry involves the relationships between a triangle's interior angles and ratios of its side lengths. The units of these lengths can be millimeters, centimeters, meters, kilometers, inches, feet, yards, miles, or even light years. The angular units are usually either degrees or radians, where there are 360 degrees or 2 pi radians in one revolution. So why is trigonometry important? Trigonometry allows us to determine distances and angles by calculation in situations where measurements are impractical or impossible. We will briefly mention some of these, including a very important discovery that has contributed enormously to our modern information and communication technologies. Trigonometry was used to sail and navigate the oceans and to explore and map the world. The British explorer and cartographer Captain James Cook certainly knew and used trigonometry as he was navigating and charting his way around the world from the Arctic to Antarctica. Today, it underpins all modern navigation such as GPS, which is used in all aircrafts and ships. Trigonometry was used to determine the distance from the equator to the North Pole along the meridian of the city of Paris in the 18th century, some 100 years before anyone ever got to the North Pole. This led to the definition of the metre, which is 1/10,000,000th of that distance. In the first part of the 19th century, the French mathematician and physicist Joseph Fourier discovered that complex signals made of non-sinusoidal waves can be constructed from trigonometric functions called sine waves. This discovery is considered one of the greatest in the history of mathematics and has had a profound effect on the information and communication technologies of the 20th and 21st centuries, as it is the basis of signal processing. A sine wave is a simple wave that looks like this. A wave that does not look like this is non-sinusoidal. In fact, the electricity that is generated in power stations and delivered to our homes, offices and factories are simple sine waves with a lot of energy. Besides employing waves to carry energy, waves can also carry information. Today, non-sinusoidal waves are information-bearing signals that are used to encode things such as voice, music, text, images, video, and other sources of information. This non-sinusoidal wave encodes the number 1 when dialing a telephone number using dual-tone multifrequency, or DTMF. The other numbers are similarly and uniquely encoded. This non-sinusoidal wave is an amplitude-modulated or AM wave that's used in radio broadcasting, while this non-sinusoidal wave is a frequency-modulated FM wave that's also used in radio broadcasting. These are examples of analog signals, but non-sinusoidal waves are also used in the digital world. This non-sinusoidal wave is of a clock signal that's used to synchronize the transfer of data in digital systems such as computers and mobile phones. These clock signals are the heartbeat of all digital devices and systems and beat millions or billions of times per second. This non-sinusoidal wave represents the capital letter R in the binary code known as ASCII, the American Standard Code for Information Interchange. The other letters and characters of text are similarly and uniquely encoded. Believe it or not, all these non-sinusoidal waves can be constructed from simple sine waves like the red one shown above. All these waves power our lives as well as keeping us connected, entertained and informed. Fourier is one of the 72 names of French engineers, mathematicians and scientists that are displayed on the Eiffel Tower in Paris in recognition of their contributions to these fields. Also, in the first half of the 19th century, trigonometry was used to finally determine the distance to the stars. This was first achieved by the German astronomer and mathematician Friedrich Bessel in 1838, when he published his determination of the distance to the star 61 Cygni. He determined it to be 10.3 light years away. That's close to the current measurement of 11.4 light years. Trigonometry was also used to identify Mount Everest as the highest mountain in the world in the mid-19th century during the Great Trigonometrical Survey of India, some 100 years before it was successfully summited by Sir Edmund Hillary and Tenzing Norgay in 1953. With all of these achievements, and many others, trigonometry has given us a sense of the size of the Earth, the scale of the heavens above, a way to power our lives, and the marvels of modern technology we take for granted. To begin our study of trigonometry, let's return back to triangles. Trigonometry has two main branches, plane trigonometry and spherical trigonometry. This video will only consider plane, that is, flat, right-angled triangles. Spherical trigonometry deals with triangles on spheres. Celestial navigation and GPS both use spherical trigonometry. It is these plane triangles that define the three fundamental trigonometric ratios of sine, cosine, and tangent. All right-angled triangles have only one right angle. And all right-angled triangles have two acute angles that sum to 90 degrees. Acute angles are angles less than 90 degrees. To understand trigonometry, we must first correctly identify the different parts of a right-angled triangle. Here is a right-angled triangle. In all right-angled triangles, the longest side is called the hypotenuse. Before we name the other two sides, we must first consider which of the other two angles we're going to reference. If the angle theta is here, then the side opposite theta is called the opposite, and the side next to theta is called the adjacent. The term adjacent simply means next to. Conversely, if the angle theta is here, then the opposite and adjacent sides swap positions. Here are some right-angled triangles in different orientations with all their sides correctly named with respect to where the angle theta is in each. Note that the opposite is always opposite the angle theta and the adjacent is always next to the angle theta. The next thing we need to understand are ratios. In trigonometry, a ratio is simply a fraction, where the numerator and denominator are either an opposite, adjacent, or hypotenuse. As there are only three sides to all triangles, and as there are only two parts in a fraction, there are only three combinations of ratios that we can construct. This fact comes from basic combinatorics. 3 choose 2 equals 3 combinations. These are the ratios. Opposite divided by hypotenuse, adjacent divided by hypotenuse, and opposite divided by adjacent. The ratio of opposite divided by hypotenuse is called the sine ratio. The ratio of adjacent divided by hypotenuse is called the cosine ratio. And the ratio of opposite divided by adjacent is called the tangent ratio. These ratios are abbreviated to sine, cos, and tan. The mnemonic used to remember these ratios is so, ka, toa. The three basic trigonometric ratios are sine theta equals opposite divided by hypotenuse, cosine theta equals adjacent divided by hypotenuse, and finally, tangent theta equals opposite divided by adjacent. These three ratios relate a right-angled triangle's acute angle with its side lengths. Each of these three trigonometric equations have three variables in them, the angle theta and a combination of opposite, adjacent, and hypotenuse. Be careful and do not make the error that the angle theta is directly equal to any of these ratios. In order to use trigonometry, we need to be able to solve each of the three equations for each of the variables in them. For the sine equation, the hypotenuse equals opposite divided by sine theta. The opposite equals hypotenuse times sine theta. And the angle theta equals the inverse or arcsine of the ratio opposite divided by hypotenuse. For the cosine equation, the hypotenuse equals adjacent divided by cosine theta. The adjacent equals hypotenuse times cosine theta. And the angle theta equals the inverse or arc cosine of the ratio adjacent divided by hypotenuse. For the tangent equation, The adjacent equals opposite divided by tangent theta. The opposite equals adjacent times tangent theta. And the angle theta equals the inverse or arctangent of the ratio opposite divided by adjacent. Let's look more closely at what each of these ratios mean. The sine ratio states that for any specific acute angle theta, the ratio of a right-angled triangle's opposite to hypotenuse will also have a specific value which is calculated by opposite divided by hypotenuse. When you see sine, think opposite divided by hypotenuse. Or conversely, when you see opposite and hypotenuse, think sine. The cosine ratio states that for any specific acute angle theta, the ratio of a right-angled triangle's adjacent to hypotenuse will also have a specific value which is calculated by adjacent divided by hypotenuse. When you see cosine, think adjacent divided by hypotenuse. Or conversely, when you see adjacent and hypotenuse, think cosine. The tangent ratio states that for any specific acute angle theta, the ratio of a right-angled triangle's opposite to adjacent will also have a specific value which is calculated by opposite divided by adjacent. When you see tangent, think opposite divided by adjacent. Or conversely, when you see opposite and adjacent, think tangent. But why? These trigonometric ratios are an extension of the idea of similar triangles. Similar triangles are triangles that have the exact same three interior angles but whose corresponding side lengths are different. The important thing to understand about similar triangles is that their corresponding side lengths are always in proportion. We will now demonstrate this property of proportional side lengths of similar triangles and how this property is generalized to the three trigonometric ratios. Here are three similar triangles: triangle AOB, triangle COD, and triangle EOF. All three right-angled triangles are similar because they all have a right angle at B, D, and F, the common angle theta at O, and the same angle at A, C, and E. This is known as the AAA similarity theorem, where the three A's refer to the three angles. Having established that these three right-angled triangles are similar, we know that their side lengths are also proportional. This means that the ratio AB divided by AO equals CD divided by CO equals EF divided by EO. We can make an infinite number of similar triangles with the same interior angles as these three, and the ratios of the opposite divided by hypotenuse of these similar triangles will all be equal to each other. That fact is essentially what sine theta equals opposite divided by hypotenuse is saying. This also means that the ratio BO divided by AO equals DO divided by CO equals FO divided by EO. We can also make an infinite number of similar triangles with the same interior angles as these three, and the ratios of the adjacent divided by hypotenuse of these similar triangles will all be equal to each other. That fact is essentially what cosine theta equals adjacent divided by hypotenuse is saying. This also means that the ratio AB divided by BO equals CD divided by DO equals EF divided by FO. Again, we can also make an infinite number of similar triangles with the same interior angles as these three, and the ratios of the opposite divided by adjacent of these similar triangles will all be equal to each other. That fact is essentially what tangent theta equals opposite divided by adjacent is saying. Here are all the ratios we just saw shown all together. It is these equivalent ratios that lead to the three trigonometric ratios of sine, cosine, and tangent. So far, we have shown these ratios in their general form. We will now look at some ratios with specific angles and ratios to consolidate our understanding. The easiest trigonometric ratio to understand is tan 45 degrees equals 1. This ratio comes from a triangle that's formed when a square is cut diagonally in two as shown. As the opposite and adjacent of this triangle are equal because they are part of a square, the ratio of opposite divided by adjacent equals 1. This is true for this triangle whose ratio of opposite divided by adjacent equals 1. For this triangle also whose ratio of opposite divided by adjacent equals 1. and also for this triangle whose ratio of opposite divided by adjacent equals 1. Note that these three triangles have different values and different units. But this makes no difference because the units cancel and the ratio of opposite divided by adjacent always equals 1. This is true for all right-angled triangles with an acute angle of 45 degrees, regardless of the triangle's size or the units of its side lengths. Therefore, when the angle is 45 degrees, the ratio of opposite divided by adjacent always equals 1. This is written simply as tan 45 degrees equals 1. The next easiest trigonometric ratio to understand is the sine of 30 degrees equals a half. Exactly half. This was correctly stated by Sheldon Cooper in The Big Bang Theory, Season 1, Episode 2, The Big Brown Hypothesis, when he and Leonard were figuring out how to lift a mattress up a flight of stairs. This ratio comes from a triangle that's formed when the length of its opposite side is half the length of its hypotenuse. In this triangle, the angle theta is 30 degrees and the opposite is half the length of the hypotenuse. This is also true for this triangle, and also true for this triangle. Note that these three triangles have different values and different units. But again, this makes no difference because the units cancel and the ratio of opposite divided by hypotenuse always equals a half. This is true for all right-angled triangles with an acute angle of 30 degrees regardless of the triangle size or units of its side lengths. Therefore, when the angle is 30 degrees, the ratio of opposite divided by hypotenuse always equals a half. This is written simply as sine 30 degrees equals a half. The next easiest trigonometric ratio to understand is the cosine of 60 degrees equals a half. This ratio comes from a triangle that's formed when the length of its adjacent side is half the length of its hypotenuse. In this triangle, the angle theta is 60 degrees and the adjacent is half the length of the hypotenuse. This is also true for this triangle, and also true for this triangle. Note that these three triangles have different values and different units. And again, this makes no difference because the units cancel and the ratio of adjacent divided by hypotenuse always equals a half. This is true for all right-angled triangles with an acute angle of 60 degrees regardless of the triangle size or units of its side lengths. Therefore, when the angle is 60 degrees, the ratio of adjacent divided by hypotenuse always equals a half. This is written simply as cosine 60 degrees equals a half. Trigonometry has many identities which are equalities that involve trigonometric functions. We will now look at and prove the first and simplest of all trigonometric identities. This identity is the ratio of sine theta divided by cosine theta. These trigonometric functions can be rewritten in terms of their ratios as opposite divided by hypotenuse divided by adjacent divided by hypotenuse. This can be rewritten as a division of two fractions as follows, and then as a product of two fractions. We can now cancel the two hypotenuse terms. We are now left with the ratio of opposite divided by adjacent. This, of course, is the definition of the tangent ratio. Therefore, the sine of theta divided by the cosine of theta equals the tangent of theta. If you've ever wondered how a calculator calculates the sine and cosine of angles, it does so with the following formulas. As complicated as these formulas appear, they only involve the operations of addition, subtraction, multiplication, and division. In these two formulas, exponentiation is essentially repeated multiplication. Also, the angle theta is in radians, not degrees, and the exclamation mark symbol denotes the factorial function. The formulas to convert between radians and degrees are shown here. The factorial function is the product of a positive integer n, and all the integers less than n all the way to 1. These two formulas were first discovered in the 14th or 15th century by the Indian mathematician Madhava of Sangama grammar or his followers in the Kerala School of Astronomy and Mathematics, centuries before they were rediscovered by European mathematicians. So how does a calculator calculate the tangent of an angle? It uses a trigonometric identity we saw and proved earlier. Tan theta equals sine theta divided by cos theta. Madhava also discovered the following arctangent formula. This formula was later rediscovered by the English mathematician James Gregory in 1671. The formula allows us to find an angle given a particular ratio whose absolute magnitude is less than or equal to 1. This formula is interesting because if we let x equal 1, then we get the following. Now the angle whose arctangent is 1 is the angle 45 degrees, or pi divided by 4 radians. We now have the following equation, known as Leibniz's series, after the German mathematician Gottfried Leibniz, who rediscovered it, after Madhava, of course. Multiplying both sides by 4 then gives us this equation. Finally, expanding the brackets gives us a very simple formula for calculating the value of pi, using only the operations of basic arithmetic. How cool is that? While this is a simple formula to calculate pi, it's not very efficient as it converges very slowly, requiring billions of terms just to achieve 10 correct digits. We hope you now appreciate and understand where trigonometry comes from and the many practical uses it has. We will leave you with a simple implementation of this formula in the Python programming language. Your understanding of mathematics is always improved when you appreciate how its rules work. If you liked this video, then please like, share, subscribe, and add a comment. You can also check out more maths videos at Maths Whenever on YouTube. And for a collection of other mathematical stuff, follow iPhi on Instagram, where I is the imaginary unit, phi is the golden ratio, e is the base of the exponential and natural logarithm functions, and pi is the ratio of a circle's circumference to its diameter. Finally, if you're a mathematics student in secondary school and would like to take more control of your learning, then the Maths Factory website is definitely worth checking out. It has a collection of maths videos to help you review a concept and how to use the TI-CAS calculator. Thanks for watching and see you next time.